So I was playing EmuDevz, which is the game on Steam where you can make a Nintendo Entertainment System emulator in JavaScript, and I finished it, and I had this thought, this awful, horrible thought. I wonder if I could make a Nintendo emulator in Haskell. And then I said to myself, nah, that's a stupid idea. And then I did it. I made a Nintendo emulator in Haskell. So this is a pretty weird thing to do, right? Haskell is famous as being a lazy, functional, mostly pure language, and an emulator is roughly, to a rough approximation, the least pure application one can write. And I'm going to jump on my soapbox. I'm going to try and not use the word pure, although I'm sure I will a few times in this conversation. An emulator is all about side effects. You are modeling some collection of chips, and the only thing you want to do, more or less, is change the values in those chips, mutate them constantly, make side effects appear on the screen, and as you could hear, in sound, and take input from the keyboard. It's all impure. Nearly everything you're doing is side effectful. So how did this happen? Let's start by looking at the code. Now, this harebrained idea began because I've been, as if you're a regular viewer of the channel know, alternating videos each week. We publish a new video here. Why am I saying we? I publish a new video here every Friday. What I've been doing is one Friday on the Haskell MOOC, haskell.mooc.fi, and then the next Friday on EmuDevz. And I kind of got to the end of my EmuDevz rope. I still had a taste to continue this way of thinking about things. And I thought, well, what if I took this peanut butter and this chocolate and mushed them together in one delicious cup? And it did turn out, in fact, to be fairly delicious. So I want to give full credit here. EmuDevz is not incidental to this. EmuDevz was the map. Playing that game or implementing their emulator according to their menu really gave me a roadmap to follow. That roadmap was in the large, first do this, then do this, then do this component. But also when I started, I said, well, I can use this structure. The way in which they're passing data around, I'm sure I could emulate that in Haskell. And that turned out not to be true. Very quickly, once I started trying to do it in this language, while the overall breakdown, there's a CPU, there's a PPU, there's an APU, while that's all still true, the way that the languages deal with data is very different. Let's take a look. This here is amusingly the nerve center of the code, even though it doesn't actually have any executable code except for, I think, one helper function at the bottom. This is all of the types, more or less, used for this program. What I'll do is I'll start by showing you the things that are similar to the JavaScript in EmuDevz, but then I'm going to call out the things that are different. Many of these techniques have been used by other people who have written Haskell emulators. I did a lot of research on how do you write a Haskell program that has a lot of state, and I had a great resource in the form of my friend Patrick, who answered many of my dumb questions and gave me some advice along the way. So you can see here we have our top level emulator record. It's holding mostly references to these various components. It has its own vector for the 2K of RAM that the Nintendo unit has built in. It has references to the cartridge and the mapper, which is a very important structure. We have references for the controller, and we have a couple of flags here, and you'll notice that these flags are in IORef. That's the central way in which we are trying to deal with mutable state. Almost every bit of mutable state in this particular emulator, with the exception of some vectors, if it's standalone mutable state, it's wrapped in an IORef. Now, I'm actually going to roll back to a slightly earlier version of the code because there is a complication in what I just showed you that I want to get into, but I want to get into it later. So let's look at how we've modeled the actual components. First off, we have a 6502 CPU. And you can see we have our registers A, X, Y. Probably a big mistake on my part to use single letter names for that, but congratulations, now we can't do the Haskell love trick of using X as a local binding. We have a stack pointer, PC flow. This is all standard 6502 stuff. Then we have the pixel processing unit, and this is just a monster structure, all sorts of stuff. And it's a very flat structure. I did not start this out as such a flat structure. I had broken it down. The loopy registers had their own thing. The sprites had their own thing. What I found is that this All of the data here is used in just extremely tight loops in drawing. I haven't done a true performance pass yet. I did one performance pass early on, and the outcome of that was to try to minimize the amount of structure traversal that I needed to do, so this is all fairly flat. Cartridge or ROM specific structures, they're all vectors. For most mutable state, as I said, we're using these IOREFs. So the main emulator loop lives in a monad, and we've called this monad emu. And what you might notice here is PPU returns this emu, but it doesn't take any parameters, yet it's clearly doing a lot of work. How the heck does that happen? And the answer is that this emu type is what we call a reader. I describe reader is that it's a global variable. This is not true. This is not a literally true statement, but it is the helpful simulation. So you can see here we have this type MUA, which is actually a reader T emulator. So this type here, this emulator type, is actually living inside the reader. And so from anywhere else in the entire world, you see PPU is an accessor on emu or on emulator. Anywhere else in the world, we can ask for any of that data. So what this frees you from is it frees you from having to thread the context through all of these things. Now, ironically, in the pixel processing unit, you're doing so much work that you actually start seeing the cost for asking for these things and unboxing them starts to become real. Outside of the pixel processing unit, even into, the CPU proper. So literally every register access on the CPU goes through the reader. That's also true for settings. So there's a lot of boxing and unboxing going on here. It's surprisingly, the penalty is not that high. I think the compiler is just doing a lot of smart things here. I've vaguely considered restructuring this to not need the reader for what I consider performance critical parts of this story. And really, what I learned is that it is fairly difficult for me to outsmart the compiler. I've had various branches of this where I've taken something that was using the reader and ripped it out and manually passed parameters around. In most cases, that made the code slower. We're getting 60 frames per second easily, and in between each frame, we're effectively sleeping for between 9 and 10,000 microseconds. There's plenty of time left over. If we start, I'm doing it again, I'm saying we. If I start encountering areas where, performance is slowing down, I might consider refactoring or doing a perf pass, but it's not, so far hasn't been necessary. The big problem is that for all of this boxing and unboxing, there is a lot of allocation going on. So I do see stalls or hangs occasionally, which are connected with garbage collection. The PPU is definitely where I had the most bugs. I feel it was the most complicated component by a New York mile. I was experiencing performance problems in the PPU, which led me to refactor it to be more flat early on. This was absolutely a mistake because I wasn't fully at correctness yet. And refactoring this into, where's my ludicrously? You could see this is not fun Haskell to write. This is writing Haskell as if it's TRS-80 Model 1 Basic, essentially. And it's extremely imperative code, and it's deeply nested, which nesting in Haskell is the worst because white space is syntactically meaningful, so it's very easy to just completely break your code. And the formatters that you can use to help keep yourself from breaking, they're all terrible. They all basically do not work when your code is not formatted correctly. If your code won't parse, the formatters are useless. And what I need the formatters for is to help keep my code parsing. So I'm very, very salty about that. I spent about half of this working in Emacs and half working in VS Code. VS Code was better suited to the task. The hottest loop in the PPU is right here, where we're actually copying pixels, individual pixels, to the frame buffer, which means a bunch of name table lookups and the like for the background. There are probably ways to fix this, but they're not mechanical. I would need to actually change the architecture of this a little bit, probably to try to draw pixels a tile at a time rather than one at a time. That would reduce this by a large factor. But as I said, I'm still getting 60 FPS, so I don't know how motivated I am to do that. So now I'd like to roll forward to talk about where we are now, which is I've just implemented save states. And save states were what I was waiting for to talk about this on the channel. Why? Not for you, but for me. If I don't have save states, then whenever I want to actually show this on the channel, I have to start the app, assuming the thing I want is at the beginning of whatever I'm showing, and then very quickly set up OBS, point at the right window, and it's kind of a pain. But if I have save states, I can just roll back to where I want to be, and that's much more convenient for me. The problem I had when I started doing save states is that my data structures meant that I was going to have to write a lot of duplicated code, and I really didn't want to. See some loopy scrolling going on there, isn't that beautiful? So let's look at what was changed. So the central problem is that in order to have save states, you have to serialize your mutable data. There's no good way to serialize mutable data in Haskell. You basically are forced to copy it to some immutable structure. So I hunted around and heard a suggestion that was so outlandish, I thought it couldn't possibly work, involving type-level metaprogramming. And the center of that is using a Haskell extension called DataKinds. And I love this because this meant that with a change to my data structures and a few type signatures, I was able to leave all of the existing code in place almost untouched. And then I had to add some new code to actually do the serialization and unserialization. But you're never going to avoid that. What I was afraid of was having to actually modify all of the code that I'd already written, and I don't want to do that. Well, you could see we're using these two type extensions, DataKinds and Type Families, and we defined this sum type, which says there are two types of state. There's mutable state, which is the live version that's in our app, and there's the snapshot, which is what we're going to serialize to our save state. And we have, you could see, four variants of this, or families, I guess they're called. And really there's two, because these are all just different vectors. And, I needed one of these for each type of vector, but you can kind of bin these together as being, we've got ones for the vectors, and then we've got ones for our IOREFs. And the interesting thing here is that through the magic of type-level metaprogramming, this means that if I say that one of my types is a mutable type, then that is essentially exactly the same as having an IOREF of A. Ref mutable of A is an IOREF of A. Ref snapshot of A, that's just an A. And all of this happens at compile time. It's just beautiful, because if you have a mistake, you're going to get your compilation error. You don't have to think about this. These types, this IOREF is just magically erased at compile time for the snapshot variant. And so that's why, if we look back at our types fields, looking at the CPU, for example, previously these were all IOREF word A, IOREF word 8. Now they're parameterized by this state kind. This type alias allowed me to keep the existing code still in place. The type signature of this didn't change at all. It's still returning the same thing. It's still returning a bunch of IOREFs. Nothing happened inside here. Really, really beautiful. The conversion took about a day and a half to do this. And most of that time was spent writing kind of extremely creepy save state code where I'm literally, snapshotting, freezing all the data and restoring it. This is code that I'm reasonably confident I could have gotten creepier about it and, done some smart iterations so that I wasn't literally, walking every value in the PPU. But by doing it this way, there's no magic, right? This is a lot of code, but it's very boring code. It's very easy to understand. And so at every step of the way, there's basically almost no moment that this code didn't compile and run, even while I was in the middle of converting these types at an extremely fundamental level. And this is where Haskell really paid off. If you tried to do this level of type change in JavaScript, or really any other language, I don't think it would have. I don't think that statement that during the conversion I could compile and run it was all fine, as long as I didn't try to, actually save a state. I don't think that would be true in almost any other language. There are already better emulators out there. There are better emulators written in Haskell. The point of this was not to write the world's best emulator. It was to write the emulator that let me do a reasonably large Haskell project. A lot of the most interesting work is saved for the end, which is implementing the various mappers. I did not understand what a mapper was in Nintendo parlance. I understood the idea of memory mapping. I mean, you have to implement it in order to make the emulator. I did not realize how complex these mappers are. So my description of a mapper, which I'm not trying to be super precise here, a mapper is simply a chip or set of chips that lives on the cartridge. And this is how Nintendo managed to keep the NES relevant into the 1990s. The later cartridges have much more capabilities than the earlier ones. It's because the mappers actually gave the cartridges more capabilities. First Nintendo cartridges, you might have, again, I apologize if I'm getting these precise numbers wrong, you might have 4K of addressable memory. By the early 1990s, they were making cartridges with 256K, but the fact that it is made with largely off-the-shelf parts, except for the mappers, which have this custom ASIC, this custom logic, to me it's really fascinating, and I was really glad to learn about it. So thanks for joining me on this adventure. This is Tea Leaves Programming. We're programming like it's 1979. Thanks for watching.